If you have an area of sheet metal you do not want to warp, keep it cool and place your copper there. Or block the area off and prevent heat reaching it altogether with correctly placed chills. Heat control. Copper wicking away heat from an area can dramatically change your weld characteristics. Let me show you what I mean. Here I have 1mm low carbon steel. I'm going to weld a lap joint with no copper backing or chill at 80 amps. As you can see, it's far too hot. It's burning through the material, blowing holes, and it's just too high an amperage, even if I move quickly. Now I'm adding a copper backing to the base metal. Keeping the amps at 80, this is much better. Although it's still too hot, the copper is drawing away some of the heat and allowing me to move at a more agreeable pace than before. The weld isn't perfect and the material is still overcooked, but it's certainly better than before. Now let's add an extra strip along the top. So we have some copper backing the base metal as before, but also a chill laid on the top sheet. The amperage is exactly the same. I haven't changed a thing. Look at the difference. The amps are much closer to where they need to be. The bead doesn't look overcooked or burnt. Although it is a little bit inconsistent, it's still a big improvement. These 3 welds were all completed at 80 amps. Let's compare several more welds at different amperages. One at 40 amps, one at 60 amps, and one at 80 amps, all without copper chills. The 40 amp weld is underpowered, while the 80 amp weld runs too hot. The 60 amp is closer to the ideal setting for this joint. Now, when we repeat the 80 amp weld, but use copper chills on both the back and top surfaces, the results significantly change. Even though the amperage is higher, the weld quality improves. If we look closely at the heat affected zone, the difference is clear. The 60 amp weld without chills shows a large heat affected zone, whereas the 80 amp weld with chills has a much smaller one. This is because the copper acts as a heat sink, drawing away the excess heat and preventing it from spreading through the material. The copper also helps protect the weld from oxidation by shielding the molten metal from the atmospheric gases. Looking at the underside of the welds makes this even more obvious. On the 60 amp weld with no copper, you can see full penetration. In fact, the weld metal has actually dropped through the base of the joint. In contrast, the 80 amp weld made with copper chills shows no burn through, minimal penetration at the base, and also a much smaller heat affected zone. This demonstrates how effectively copper chills control the heat input and the overall weld quality when used correctly. Now, if you're thinking, why is it showing me this? Surely it's best to just not use copper and dial in my settings. This is just something that has to be considered when using chills. It will affect your welds and you need to account for that. But sometimes you need to use copper to perform the weld, and I want you to know how things can be affected by the material before you just go ahead and start using it. So when do you need to use copper now that you know how it will affect your welds? Prevent blowout. Hacking your joints with copper can reduce the chances of your weld pool sinking out the root of your joint. When would this happen? When welding open corner joints, so outside corners. Placing copper on the inside of the corner can not only stop you blowing out, but it can also help keep the inside sharp and ward off any excess intrusive penetration without actually lacking said peno or fusion. Let's take a look at some examples. Here, I'm welding an outside corner. Again, it's thin sheet, but this will help with any sheet size 3mm and below. Raw dog, no chill or backer plate. I manage it okay, but I had to take some time previously to dial in the settings, and I risk going too hot and blowing out the joint when selecting. I also have to run it very cold. This, of course, would be easier with pedal TIG, but it can be much less consistent. Here, you can see I'm using copper. The settings don't matter as much going in, as the copper will allow me to sort of test the water without that same danger of blowing out as I had before. I can go in much hotter, improving fusion fabrication without burning through or causing a mess on the inside. As you can see when I turn it over, it has no sag or dropout. So if this fabrication was a biscuit tin lid design or something similar, I don't need to waste time filing it out. Oxidation. Copper can be used as a shield to prevent sugaring when welding stainless steel or other vulnerable alloys. Yes, you can use argon purges to prevent your penetration or the back of your root joint oxidizing when welding stainless steel. However, this can get expensive. If it can be replaced with a copper back, you should do so. Copper backing when welding stainless will stop the gases in the atmosphere getting to your root, where your material is either molten in the form of penetration or past its temperature point of oxidation. You will severely impair the performance of your welded joint by not protecting the interior from oxidizing. And a simple copper strip can do that. Okay, it all depends on requirements, but typically you're aiming for full penetration, no sugaring, and no sagging or dropout. This can be difficult with stainless as the alloy severely reacts to minimal amounts of oxygen. Not only is sugaring ugly, it will cause weakness and be unsuitable for any application that requires stainless steel, as it will corrode further over time, even if it's cleaned with a passivation process. You're watching this video to improve your TIG welding. So here are some small changes that will drastically improve your welding skills. Watch this next video to see those. For an in-depth look at stainless steel, drop me a comment telling me what you want discussing, and I'll make a video regarding purges and their uses. So subscribe so you don't miss that one. Enjoy.